Okay, so just consider a permutation of that number. And what I'm going to look at in this permutation are longest increasing subsequences. These are the subsequences of the permutation, which are increasing. So, for example, out of the first, fourth, and seventh entries, and 4, 5, 7 is increasing. And these are of maximal length. Okay. So the longest increasing subsequence you can find in this particular permutation is length 3, and there are 2 such increasing subsequences, 4, 5, 7, and 4, 6, 7. Okay. So that's the object. And just to introduce the notation, I'm going to call L of sigma the length of the longest. So here 3. And you can think of the subsequences themselves as functions. Yes. And now that I see it, these are of course not the same permutation. So there's so not an exhaustive list, but ignoring that, 3 is the correct answer. Okay, so this is Ulam's problem. So he asks the following question. So now pick a permutation uniformly at random. So look at all n element permutations and pick each of one of them with probability 1 over n factorial. And you want to understand what is the length of the longest increasing subsequence. So this problem has kind of a funny history. Ulam did not propose this in a research paper. He put this as an exercise in simulation, in Monte Carlo simulation, in one section of an engineering textbook that he was involved in writing. And thought, okay, this is something that an engineer could learn how to simulate and get statistics with its value, and then maybe it'll so unsurprisingly, no one picked up on this for a while as an interesting math problem until Hammersley started thinking about it in 1972. And he showed the following thing. And this is already fairly non-trivial. So he figured out the correct order for this length, L of sigma. And he showed that if you scale it by, so he showed the correct order is root n, and that if you scale by root n, then as n goes to infinity, this converges to a constant c. So I'm not so concerned with the exact type of convergence, it's convergence in probability, but just think that this guy here is clustering, it's very likely to be very close to the point c, even though it's a random variable. And he didn't show what C was. That's a harder problem. Ulam in 1961 suggested something like this might be true with C equal to 1.7. Okay, so Ulam was wrong. His simulations only went up to like n equals 9, and so it's unsurprising that he guessed incorrectly. And this is with the work in the later in the 70s. This is where I think things really take off here. So Logan and Shep, and separately Rashid and Karov, showed that C equals 2. And the story here is that this problem can actually be solved using this combinatorial correspondence called the RSK bijection. And so you really have basically an exact formula for the probability distribution for L of sigma. Okay. And so you can do some analysis of this formula and figure out what C is going to be. Okay. So it's not something I'm really going to talk about throughout the talk, but underlying all these results, there is some exact combinatorics with formulas that you can work with, which actually allow you to prove. Okay. So I would call this result a law of large numbers. So this is like the analog of the classical law of large numbers, but for longest increasing subsequences. So the next thing you want to do as a probabilist, once you establish a law of large numbers, is to try and establish a central limit theorem. Okay, so the classical central limit theorem would say that if you usually says something like this: take the thing that you care about, which is in this case order root n, and often the fluctuations around the thing that you care about are square root of the leading term, and often the fluctuations converge to a Gaussian random variable. So this is already a very different situation, and this is realized by exactly enhanced by some much more involved understanding of that formula. So let me point out two things. One, the size of the fluctuations here is not square root of the leading term, it's cube root of the leading term. So already something interesting is going on. And in the limit, you aren't seeing a Gaussian random variable. So rather than the fluctuations here looking Gaussian, the fluctuations are looking like something called a Tracy-Woodham random variable. And this random variable had appeared earlier in the context of random matrix theory. So, which is a connection which is actually still very mysterious. Really, you can see it by recognizing that the formulas take you to the same place, but it's not clear why this problem has anything to do with random matrix. So I'll say you also see this same limit if you take a random n by n Hermitian matrix and look at the top eigenvalue, the fluctuations of the top eigenvalue also obey this same law. Okay, so what's left? So I think of this kind of like in probability, you're taking like a standard probability sequence, you go law of large numbers, then central limit theorem, and then maybe you try and understand some functional convergence and you understand Brownian. There's kind of an analogous problem you can study here. This should be added on elsewhere. So you could ask, what about the actual increasing subsequences themselves? Okay, so now these are random functions. And you can ask, do these random functions themselves have an interesting one? This is something that myself and Duncan Dauvergne recently established, that if you look at this as a random function and kind of rescale the domain, so that the domain is the unit interval 0, 1. At first order, basically what you just see is a linear function. So it's kind of increase something, so that's surprising. But if you look at the fluctuations around this linear function, what you see is an interesting new object. So you see a random continuous function phi. So you have some in the pre-limit. These INs are just some discrete function. They're increasing. You subtract off the linear terms, so now they're going to be able to go up and down. And you kind of rescale the domain and rescale the codomain. You end up with some interesting one. So what usually happens in probability in these situations? The first guess would be, okay, we have a function going from 0, 1 to r. Our first guess should be maybe this is like a Brownian motion or a Brownian bridge or something like that. It turns out it's much smoother than in Brownian motion. So Brownian motion is like Holder almost a half. So it's Holder half minus epsilon for every epsilon. This guy here is Holder almost 2/3. So Holder 2/3 minus epsilon for all epsilon. The other thing that happens with Brownian motion is the increments of a Brownian motion are just independent. Of course, you can't really see from the simulation here, but this has a complex correlation structure. Okay. So all of this suggests that there's really something more interesting going on with the problem than what you usually see with just sums of independent variables. So what has to happen is the moment you see, for example, you see fluctuations which aren't on this square root scale, or you see limit objects with funny correlations, there has to be some structure to this problem. And that's really what I want to talk about. So this is an observation that goes back to Hammersley, which is that this longest increasing subsequence problem posed by Ulam is really a random geometry. So what I'm going to do is I'm going to look at I'm going to take my permutation, and I'm going to look at its graph. So sigma of 1 equals 4, sigma of 2 equals 1, and so on. And what I can do is I can think of these points just sitting in the plane, and I can identify L of sigma in the following way. So if I look at all paths starting in the bottom corner here and ending in the top corner there, so these are paths that just go up and to the right, then this length, L of sigma, is the maximum number of points that I can fit onto one of these upright paths. So in other words, think of all of these upright paths as having a weight, which is just the number of these points that sit on those upright paths. L of sigma is the weight is the heaviest weight of a path. Yeah. So if you, it's really, think of this almost like a metric, right? So in a metric, you have paths with length, and the distance between pairs of points is the minimal length path, is the length of the shortest path. Here, it's like a metric, except things are flipped on the top. So we look at the length of the longest path. Okay, so what Harris realized is that when sigma is chosen uniformly at random, you can actually put all of these longest increasing subsequence problems in one big framework. Okay. And the idea is to use a Poisson process on the plane. So what is a Poisson process on R2? So if you haven't seen this before, you'll draw something here. Imagine I take an n by n box, okay, and I put n squared points in this box uniformly around all places with equal probability. Then I take the side length n off to infinity, and I get a process of points on the entire plane. So they're uniformly distributed on the entire plane, so that the typical number of points per unit area is 1. So that's a Poisson process. Okay. So in this Poisson process, I can do the same thing that I did with the permutation. I can look at 2 points that are ordered in the right way, and I can say that the distance between those 2 points is the maximum number of points I can fit on an upright path. So if I give you 2 points in R2, the coordinates are ordered in this way, I'm going to call this distance the maximum number of points I can put on an upright path. So in other words, think of this as the length of the path. And dp is what's often called the Poisson last passage time. So again, it's not quite a metric, but it's metric-like. So in particular, it satisfies a triangle inequality. But the triangle inequality goes in the opposite direction of the usual triangle inequality, because we're maximizing over paths rather than. So how does this connect to the longest increasing subsequence problem? So the claim is that if you want to study longest increasing subsequences, you can forget about permutations at this point and just study this guy. And here's how you do it. So what I'm going to do is I'm going to take my Poisson process in plane. So this is just dots distributed uniformly in the plane. And I'm going to grow a box. So I'm going to grow an m by m box. And I'm going to stop the growth of that box when I see exactly n points in my box. So this will usually happen when the box has area equal to n. So it should have sort of side length root n very roughly. So then if I look at that box, this is now a box of random size, but it has exactly n points in it. And because of the way in which I threw my points down in the Poisson process, the relative order of the ordering of the y coordinates of the points is completely independent of the ordering of the x coordinates. So if I look at the permutation given by comparing the y coordinate ordering to the x coordinate ordering, I get a uniform permutation. So what this says, think about it a little bit longer, is that if I define the corner of my box as Tn in this way, then the distance in this Poisson last passage problem between 0, 0, and Tn is exactly the length of the longest increasing subsequence in a uniform permutation. And a maximizing path between these 2 corners, or in other words, a geodesic, is going to correspond to the function itself. That corresponds to the actual increasing subsequence. So you need to, there's a few little changes you need to make, but morally, and certainly when we kind of take n to infinity, everything works out. So here's the picture. So I take my Poisson process, I kind of tilt it by 45 degrees, and I see this. Now these upright paths just kind of look like graphs of one Lipschitz functions. And this guy appropriately scaled converges to I. So how would you want to prove something like this? So the way to prove this is, what you should try and do is take the richest possible limit of this entire Poisson last passage process. So rather than just focusing on the limit of, say, the distance between two fixed points, or the limit of just the optimizing path, we're going to try and take a limit of the entire kind of metric space. And so that's the idea. And this limit is the directed landscape. So let me explain how this works. So when I take a limit, I can tell the parameter I'm taking to infinity. So for me, that's going to be n. And what I'm going to do is, in this, I'm going to look at points that are kind of order n apart in some main directions. This main direction is going to be order. And what happens is, if you look at points that are order n apart in this way, and you look at the optimizing path between these 2 points, you see the following thing happen. So this width is like n to the 2/3. And the fluctuations of the distance, and say the distance between these 2 points, between say 0, 0 and n, this is basically a constant times n, plus a random term, which happens at the order n to the 1/3 scale. So what this suggests is, if you want to see an interesting limiting object, what you should do is the following. I'm going to keep looking at points which are aligned in some main direction. But I'm going to allow the second coordinate of those points to move back and forth on this n to the 2/3 scale. So the scale at which the geodesics are moving back and forth, that's kind of the right scale for seeing an interesting thing. Because with the idea being that distances are related in an interesting way exactly when the geodesics have some kinds of interacting in an interesting way. Okay, so that's what we're looking at here. So I take my Poisson last passage value, I subtract off the typical terms. This is like your law of large numbers term. I rescale by this n to the -1/3, and I see a limiting object. So this L is the directed landscape. And at the level of this theorem, you can just think of this as a random continuous function. And it's good also to think of it just like we think of Poisson last passage as a kind of metric. Think of this as a kind of metric. So it's assigning distances to pairs of points in the plane. And in Poisson last passage, we had this rule that our points needed to be ordered in a certain way. That manifests itself in the limit in the following way. We can only assign distances when the second coordinate s is less than. So usually we call these suggested by the notation the second coordinates of time coordinates and the first coordinates of station. And so what is this limit pi? So the scaling limit in this theorem is exactly a geodesic between 2 points in this limiting structure. So mostly what I want to do for the rest of the talk is kind of explore this object L and hopefully give some intuition for what it looks like and how it relates to just try and give some intuition for what it looks like. But before doing that, we need to kind of have a bit more motivation for studying it. So this is one particular model of random geometry where we see this directed landscape in the limit. But the idea is that this should show up everywhere. So this is this idea of the KBC universality class. So I think of the KB's universality class in the following way. So here's the idea. If I define for you a metric on the plane, where I base my metric on some independent norms. So here in the Poisson picture, I'm throwing darts at the plane uniformly at random. So I'll have, the number of points in my process that I see in one part of the plane is independent of the number of points I see in the other. Okay. So if I build a metric in this way, then it should always converge to n. And certain features don't matter. So here in the Poisson model, I'm looking at longest paths, but I could just as easily have looked at shortest paths in a different model. It was not able to do that, and I should still expect to see the same thing. And the other thing I should mention, though, it's not going to play much of a role. Often when you see people talking about the KB's universality class, they talk about interface growth. So what do I mean by interface growth? So say I give you some model, like I spill coffee on a piece of paper. So this is a homemade coffee stain. What you'll see is that the stain kind of spreads out. There's this rough edge around the coffee stain. And the way you can think of something like this is that the growing coffee stain, really think of this as a growing ball in a random metric space. So this would be, so in this picture, there's some underlying metric space. And what the shape you're seeing is, this shape is exactly all the points that are accessible from the origin, with distance less than or equal to some t. So there's this duality between metrics and these kind of interface growth points. Okay? So these are often the things that people think of like physical models for this KB's universality. So coffee stains, tumor growth, forest fires. The thing that this is named after is called the KBZ equation. KBZ or Cardar-Parisian jam. And it's some stochastic PE, which is fairly hard to define, a little bit definitely hard to understand rigorously. I'm not really going to talk about that, but that's kind of where this area is. And again, I usually don't think on the independent growth side. So I think in terms of these random metrics. So imagine the picture that I have in my mind is, you have some mountainous terrain. You have sort of mountains causing it to be difficult to move between different places in your terrain. And these mountains kind of behave like independent. So these random metrics are kind of like moving through some mountainous terrain in space. Just to give another example, here's a random metric model which looks a little bit different from, this is a true random metric model, unlike this Poisson model. It's also suspected to have the same, I expect it to have the same limit. So you could just take Z2 and do something very simple, which is I just flip a coin on every edge in Z2. And if that coin lands heads, then I say that that edge has length 1. If that coin lands tails, I say that edge has length 2. Okay, so this turns Z2 into a graph with random edge weights. You look at graph distance in this setup. So this is some discrete model of the random plane. You look at graph distance in that model, that should also converge to one. And I should say, so this model, this is something called first pass percolation, and no one has any idea how to attack it, how to prove sort of these fine theorems about it. So this is kind of where there's this underlying exact solvability in confidence works that works in this funny Poisson last passage model that completely fails for some reason. All right, so when I first started thinking about this area, the main thing that I think kind of the first question that a lot of people have is what's going on with the scaling. So we have these two exponents that are coming in. So I'm looking at points that are about order n apart, and I have these two exponents, right? So the size of the fluctuations of the distances is growing like n to the 1/3. So I'm going to call that fluctuation exponent 5. n to the chi, so we expect chi to 1/3. And then there's this wandering exponent c, which we expect to be 2/3. So n to the c describes how far the geodesic between these 2 points wanders from the corresponding straight line. And there should be some natural reason why we see 1/3. I should say in practice, it's very hard to prove anything about these, and it's coming from combinatorics, but hopefully we can at least give a kind of physics to this. So here's the goal, and if you can present a proof of these two things that doesn't rely on some exact solvability, that would be fantastic. The goal is to prove two relations. So two simple equations, which together imply these. So the first relation is what we call the shape relation. Sometimes I've seen this called the KPC relation, but it's a little bit more general. So this actually holds in all dimensions, and it's based on the following. So if you look at the boundary of a ball in a random planar metric, then what you should see is a nice function. It should look basically, it might not look exactly like Euclidean ball, but it should look, it should be differentiable and strictly convex at first order. So that's the solid red line. And the true boundary will fluctuate around that solid red line at a window which is the size of the fluctuation. So that's this dotted red. Now, how can we use this? So now say I want to understand how the wandering exponent and the fluctuation exponent are related. So imagine I pick 2 points. I have a black point and I have a red point. And what I want to see is what is the midpoint of this geodesic. So where does the geodesic cross the halfway line between these 2 points? So what I should do is the following thing. I should look at all distances starting at the black point and ending at that line, and all distances from the red point and ending at that line. So that's the red wiggly curve and the black wiggly curve. And if I believe in this, nice differentiability, strict convexity idea, then these curves should lie in sausages of width n to the c. And they should also, at least locally, they should look like parabolas. And so you can ask, well, what is the maximum of the sum of these two guys going to be? So where could the maximum of the sum possibly go? It's going to come in a random location. But the location should be in some part of the plane where these two sausages are actually overlapping. So it should roughly be kind of equally distributed in this region where the two strips overlap. So if you just build off of that, and if you assume these are parabolas, assume the sausages have width n to the c, the overlapping region has width n to the chi, the overlapping region has width n to the c, you get a little relation. This should hold in some generality. This has been proven using this sort of heuristic in some models, but it's still actually quite hard. The second relation is stranger, and this one is very specific to dimension 2. Okay? And the heuristic is shakier for sure. So here's the idea of this second relation. So this should say that c equals twice 1. So 2/3 equals twice 1. So the first idea for this relation is that if I start at base 1, I'm going to start at a base 1 and I'm going to look at distances to some horizontal line, so traveling transversely to the typical direction of the geodesic. The claim is that these increments are roughly independent, and that therefore this whole curve that I'm tracing out should look like a nice round. And the idea is coming from planarity. So basically the idea is that if you draw this geodesic to the midpoint first, then the geodesic to the left point and the geodesic to the right point have to use either side of the plane, split by this middle geodesic. The idea is these guys, this increment is coming from optimizing over this half of the space. This increment is coming from optimizing over this half of the space. And the two halves of the space are independent because we're building it off of independence. So that says that E and A. It's a heuristic. It's not exactly true. And the reason that this failed, the main reason this fails to be exactly true is because we're not dividing the space into two deterministic pieces. We're dividing the space into two random pieces. And the random pieces being split by this middle geodesic are heavily correlated with this middle geodesic. Nonetheless, we believe in this heuristic, and in some cases it's been proven using combinatorics rather than this. Okay, so say you believe that this path is just a random walk. Well, then what you should think is that the scale at which we expect our distances to decorrelate is the same as the scale at which we expect our kind of geodesics to typically wander back and forth. Okay? And we know that our distances will decorrelate when the difference between this point and this point over here, the variance of the, or the kind of typical fluctuations between that guy and that guy look like n to the pi. And if this is a random walk, that should be square root of the length there. So that gives you that second. This is not supposed to hold in dimensions higher than 2. So this is supposed to be a really planar argument. The idea being that we can cut the plane in 2, but if you do this in higher dimensions, there's no cutting of your space. And it's actually a very good and extremely difficult open problem to try and understand what would these exponents even be in higher dimensions. So if you do this in dimension 3, no one really knows what's going on. There's a general belief that the fluctuation should decrease as you increase your dimension. If they go 1/3, 1/4, 1/5, it's not going to be this. But no one has any idea how to actually put that. All right, so now we kind of hopefully have some idea for what's going on with the exponents. Let's try and understand the landscape using these exponents. Okay, but the first thing we're going to do is, rather than looking at the directed landscape, I'm just going to apply the scaling that I had in our theorem to the usual Euclidean metric. So if I do this with the usual Euclidean metric and figure out what the limit of these dn's is using a Taylor extension. So dn converges to this nice simple function, x minus y squared over 2 minus s, when s is less than t. And it converges to infinity if s is bigger than t. So I want to point out a couple of things here. So when I'm doing this scaling of the Euclidean metrics, I'm subtracting off a term which changes sign if I flip s and t. So the L2 norm here doesn't change sign if I flip s and t, but this guy changes sign. So that means we should expect that. So that means each of these dn's is no longer symmetric. So we've lost that metric property the moment we do the scaling. But it's important actually that this doesn't come with an absolute value here, because we need that this term is additive. The reason we need that this is additive is because we want these dn's to preserve the triangle. So when you're doing this sort of scaling of a metric, you have a choice. You either get to keep the triangle inequality, or you get to keep the symmetry, but you can't keep them. And the triangle inequality is somehow that's the key metric property, so we choose to keep the triangle inequality. So this limiting version of the Euclidean metric is asymmetric. So the way we've scaled E still satisfies the triangle, but it's not symmetric. So we say that E is something called the directed method, basically just a function satisfying the triangle. But we're going to think of it in terms of E. Okay, so you can define path length in E, right? So if I give you, well, what should a path be in this limiting? So a path in, the usual R2 would just be some curve in the plane. But here we have this asymmetry, which means that we are only allowed to have finite length if we move forward in time. So our paths should be actually one parameter. So they're functions from an interval st to r. And we just define this length by approximation with straight. So you can, this is a slightly more involved exercise than the previous Taylor expansion. This gives you a theory. So you can say that even though this is not actually a metric, you can still talk about geodesics. So a geodesic would just be a path. Length is the distance between its elements. So geodesics in this world are straight lines. So it's really a simple one. Path length is given by the inertial energy. Geodesics are straight lines. We have this asymmetry, but it's not really something to worry about. Nice difference. Okay, so then what is the directed landscape? The directed landscape, you should think of it as this Euclidean metric, this scaled Euclidean metric with inertial energy paths plus a noise term. And I'm going to start by understanding this at just a fixed point. So if I fix my point U, then L of U is exactly, it's basically just this Euclidean metric E plus some rescaling of a Tracy-Widdor metric. As you start to vary these points, these random variables here have some really interesting correlation structure. That's hard to understand. But for a fixed point, this is what you see. I'll point out this other thing, which is L is not E plus something, it's negative E plus. So this is an artifact of, it's kind of an artifact of the way the field began, by thinking more about these models where you maximize paths. Sometimes you could think the whole thing would be more natural to define it with a negative sign, but it doesn't take too much work to get used to that. So just like you can think E is a directed metric because it satisfies a triangle inequality, L does the same thing. So L also satisfies a triangle inequality, and it also has this asymmetry. So just like E, if you take 2 points where L is defined and flip them, then here the natural thing to say is that there L is equal to negative. Okay, so let's try and understand what are the similarities and differences between these two authors. So I'm claiming that L is kind of a perturbation in this limit. But really the structure is a lot different. So the fact that E is showing up in the definition of L is really just, the way you should think of that is saying that L is respecting that there is a Euclidean plane underneath it. But it's doing much more interesting. So the first thing we've already seen that is kind of a trivial difference. That E satisfies the triangle inequality and L satisfies the factors. This one's already a non-trivial difference. So E is a non-negative function that L is signed. So this is a property, if you throw out the symmetry condition in your definition of a metric, then there's not really a need for a positivity. Okay. So the issue with having a negative distance, right? If I have a metric, the issue with saying that I can go from point A to point B, and it takes length -1, is that then you could say, okay, well then I can go back, and I can go from A to itself, and it takes length -2, and I can keep looping around, and I get that the distance from A to itself is negative infinity. But this requires the symmetry condition. So if you throw out symmetry, it's perfectly reasonable to say that you can go from A to B, and that distance is negative. E is a nice smooth function, L is rho. Okay? So this noise that you put on top of your Euclidean metric E makes L, holder almost a half in X and Y, and actually only holder almost a third in S. So it's a rough object. This always happens with scaling limits. They're not going to be nice. So here, this is the same level of continuity as the Brownian motion. You vary X and Y, and in fact, if you just fix all your coordinates and fix 3 of your coordinates and say just vary your X coordinate with this function L, locally you see something that's really similar to a Brownian. Kind of, in particular, it's locally absolutely continuous with respect to the law of the motion. So E has all these natural symmetries. So for example, if Q is any positive number, I can write this. For E, I have this kind of flip symmetry. There are many others. L satisfies all the same symmetries as E does, except it has to satisfy these. Okay, so if I take L and I do some kind of funny rescaling like this, then notice these exponents, Q to the 1, Q to the 2, Q to the 3, these are shadows of the end of the 1/3, end of the 2/3 exponents. I see the same object. I see the exact same object when I do this with my simple metric E. When I do this with L, I see the same object, but only in this group. Okay, so now let's, things get more different when you start to think about paths. So let's think about paths a little bit. So say I give you a fixed path pi. In this Euclidean version, the length of pi is just a Dirichlet. Okay. We can similarly define its length in the directed landscape. So what do? We do the exact same thing we did in the Euclidean setting. So I have my start point, I have my end point, and I approximate the length by just summing up the distance on finer and finer curves. Unlike in the Euclidean case, I don't get a closed formula when I do this. I don't end up with some nice integral. And in particular, what happens is if I do this with any deterministic path, I'll end up with minus infinity. So what has to happen in L is, of course, there are uncounted many paths that you can draw in the plane. Most of these will have length minus infinity, but a few special paths will have finite length. So the idea is that these are very rare. But nonetheless, special paths exist, and you do see geodesics. So a geodesic, again, would just be a path whose length is the distance between its ends. Okay. L going from pi of f mass up to pi of. So these things do exist, but they are random. So geodesics in E are straight lines, but geodesics in L are rough. Here's something that's kind of nice. So if you look at a fixed pair of points, then they're connected by a unique geodesic in E, and almost surely connected by a unique geodesic in L. The picture is this. In E, of a simple geometry, geodesics are straight lines. In L, I also typically see a unique geodesic, but now it's kind of rougher. Now, one difference here is that in L, we said that we first are fixing the points, and then we're saying the geodesic is unique. So then you can ask something like, well, is it the case that you can move the almost surely in front of fixing the pair of points? And this is non-trivial. This is an interesting question because there are uncounted many pairs. So this is not true in L. So every pair of points in E is connected by exactly one geodesic, just like in the previous claim. But there are exceptional points in L connected by 1, 2, 3, all the way up to 9 geodesics. You see actually all of those possibilities, but they happen on rare sets. So if you pick a point sort of uniformly random in the plane or uniformly random in some complex set of the plane, then you'll see a unique geodesic connection, but you'll see kind of special points which are connected by up to 9. So a big difference between the two. And this is really the picture. So here's my base point in E. And I draw my 5 geodesics up to these 5 ending points. And all of these will be completely disjoint. They're just straight lines. In L, you can think of this kind of like a river system, right? So not a perfect analogy, but imagine that this is the top of some mountain, and then I have some rough mountainous terrain, and I have I want rivers flowing down from the top of my mountain to 5 finishing points down here. What happens is the noise in L is very rough, and so there's only a few good places to actually put paths. So in particular, what happens is paths will like to stay together for a while, and then they split up. Okay, so you have this coalescence phenomenon with your paths. And you can kind of think of this in relation to the statement on the previous board, that if I draw a deterministic function, if I draw a deterministic path in L, then what happens is its length is typically infinite. And this is kind of a stronger manifestation of that. Is not only are most paths have infinite length, but actually in order to get geodesics, we can't even take separate paths. We really need to take exactly this. So geodesics and E typically overlap on points. On an L, they're overlapping on these full intervals. Here's a stronger thing. Did I give you two boxes? Of course, in deterministic geometry, I can just draw many straight lines that are disjoint between these two boxes. But what happens in random geometry is things need to coalesce. So I might be able to get a few disjoint paths, but I can only do this with finitely many paths. So once I draw maybe 10 paths in between these two boxes, every other geodesic between points in here will need to coalesce with one of these guys at some point. Very strong. Okay, so this is now going back to the previous board. So we said there are points in E, there are points in L connected by up to 9 geodesics. And so you could try and do a full classification of these types of exceptional. So you could ask, for example, about the following. Can you have points in L? This would be a point, 2 points in L, P and Q, connected by 2 geodesics like this. Maybe you can have points that look something like this. You want them to come, and the goal is to come up with some natural classification of the sets of geodesics. I'm calling these are called geodesic networks. And so this is something I recently proved, is that you, up to some like natural notion of isomorphism of these guys, there are exactly 27 possibilities of this. And each, when you're familiar with these things, each is going to come with its own Hausdorff dimension. Some of these options are going to be more common. So this is your typical unique option. And these are roughly, not exactly, but they are roughly listed in increasing order of priority. So these two options on the end, I think all of these options on the end, for example, there are only countably many pairs of points. Similarly for some. So, okay, so I will stop there.
Any questions for the speaker? I can start with the question. You say that like this first passage percolation should be converging to the directed landscape.
Yes.
Can you say a little bit more about the sense in which that should be true? I'm somewhat confused about like the fact like first passage percolation is an actual metric instead of this directed metric.
So you should think of this again. Think of this like with the convergence of the Euclidean metric. So why don't I try and draw a picture? So somehow like the directionality arises as we try and take a limit. So when we were working with the Euclidean metric, in order to see a limit where we had the triangle inequality, adding directionality was forced upon us. The same thing should happen with first passage. So this is this model of that I put up with the coin flips of either length 1 or 2 on the edges. And in theory, geodesics get that sort of model. Especially if you allow more general edge weights to do things like this, right? So that's a candidate geodesic. But what should happen in your scaling limit is at the scale that we're looking at, these what I might call backtracks should just flatten. So the backtrack should get smaller and smaller. So maybe this is like this one down here is maybe n to the 2/3, and this here is n. So the size of the backtracks should probably be, well, it will certainly be, the size of the backtracks will certainly be below that, but it's probably probably like log, I guess. The true size of your maximum backtrack probably. I'm not really sure. But definitely middle of it. I mean, there's other things that happen. There are other things that are happening in some of these pre-limiting models that are lost in the limit. So another thing that's happening if you think about this longest increasing subsequence problem. The longest increasing subsequence. So say I give you some permutation. So I can draw multiple longest increasing subsequences, right? And there are many such things. And you can ask, well, which of these guys is my scaling limit talking about? Which of the subsequences? And it's kind of talking about all of them. So you'll have exponentially many longest increasing subsequences as you increase n, it'll grow exponentially in n. But all of the subsequences are sort of, if this is order n to 2/3, the subsequences are kind of clustering together at a scale which is supposed to be, I think, order n to 1. Okay. So this is another phenomenon that's possible. Hopefully that says something about first pass regulation. It's one of the reasons first pass regulation is not harder to set. One of many. Yeah, but yeah, directionality should show up as you do. Questions?
You're curious to take arguments for 9 dimensions.
Yeah, there are. So the last time I talked about, the last time I talked about this geodesic network problem, I was in the Rocky Mountains, and if there's a point in the Rocky Mountains, so this is maybe where. So you have multiple oceans. I have the Pacific out here, I have the Atlantic, I have the Arctic. And there have to be, so you can ask if I, start a river at some point, which of these 3 oceans is it going to flow in? And so if I start close to the west coast, I will flow into the Pacific Ocean. And then there's going to be some region where I flow into the Atlantic Ocean. I'm not doing an exact geography lesson here. And then there's going to be some region where I flow into the Atlantic. And if you think about it, these 3 regions, there has to be a triple point for all 3 of these regions. And at that triple point, what that means is I'm going to have, at that triple point, I'm going to have rivers that flow in each of these 3 directions. So the idea of this is it's kind of similar to what happens in the directed landscape. So there should be so let me draw what the setting for 9 geodesics is. So 9 geodesics looks like this. You have 3 ways to exit your base point, and then they all come together. And you have 3 ways to enter your final point. So let's just try and get half of this picture. So the hard part of getting this picture to work is actually getting to see that there are points where you have water flow coming out in all 3 directions. It's not a full heuristic, but that's some of the hardest things. So you can do some modification of this argument to produce structures that look good. It doesn't explain all of the pictures, but it gives some sense of kind of what some of the hardest, the rarest structures is. Well, 3 is the maximum number that you're somehow guaranteed by geometry. So as to why you never see points with more than 3 reversible economics. I mean, you could, but it doesn't happen. You need to do a different type of argument. Because, I mean, of course, I can easily draw a map with the degree 4 vertex, where I have flow and 4 in the direction. Maybe then theoretically, at least you could think that this is somehow not a generic situation, whereas this is a forced generic situation.
Any other questions? Okay. Thank the speaker again.